Thanks for attending this session on sensor programming with MRAA. And really, today I'm going to do a rerun of the presentation I did at Embedded LinuxCon Europe week ago, 2 weeks ago. So apologies for my slides, just that template. I didn't really change them, but they'll hopefully be just as informative. So I'm Brendan Foll, and I'm a software architect at Intel in Munich, Germany. And I work on the Linux and IoT application development, and essentially trying to make it easier for developers to utilize our hardware. And part of my job is working on the MRAA and UPM sensor abstraction frameworks. And so today I'll be talking about some of the new works we've been doing around security enforcement at the MRAA layer. So hopefully it'll be interesting. So the agenda today is going to be talking about what's MRAA, what's MRAA.io, what's Libmraa, and we have a lot of names. And the difference is that really MRAA is the project name, MRAA.io is the API specification, and Libmraa is the Linux implementation of MRAA. Now, really, we'll be talking mostly about Libmraa today, not about any of the other implementations we have. But just to let you know, there are some other implementations of MRAA.io around. Then we'll move on about what it does, where it does it, and why it does what it does. And then a little bit about the kind of basic API, what it looks like, if people haven't used it before and haven't seen it. And then we'll move on to basically some of the more advanced things we've been doing, and that's where the security enforcement comes into play. So some of the work we've been doing with Google on the peripheral manager or PIO framework, and then moving on to some of the more recent stuff we've been doing with AGL's AFB bus. So that's the AGL is the Linux Foundation consortium for automotive grade Linux, and it's used mostly at the moment for in-vehicle infotainment. But we've been looking at AGL's application framework bus, I think it's called, which is really a kind of lightweight JSON-based message passing bus, which we've been using to do some I/O, and I'll try and talk to you guys about how that works, and obviously some of the future plans we have, and what we're doing and where we plan on going. So what's MRAA.io? The kind of real basic. I'll try and go through that quickly. So what it really is, it's a simple Linux user space I/O protocol abstraction for things like GPIO, I2C and SPI buses, ADCs, PWM pins, and UART buses, and then we have some UART one-wire emulation. And the real idea is that it's made for monkeys. That's what the M, so MRAA doesn't really stand for anything, but the M kind of stands for monkeys, and the idea is to keep it as easy as possible. You know, the aim is to not complicate things. Previously, we said made for Neanderthals. We're trying to make it even easier now. And that's because a lot of these I/O really low-level abstraction layers are actually really complex to use. And we really want to make an Arduino style really easy to use. The easier, the better. And because of this, we sacrifice things like performance. We'll sacrifice a bunch of other stuff. But that's really the aim. And we have bindings for a load of different programming languages. So the base binding is for C, and that's probably our most commonly used and best supported API. But we also have bindings for Python 2 and Python 3, Node.js, Java, and then some experimental bindings for things like Ruby, R, Go, even PHP, Haskell. We've got a bunch of different ones people have done in the community. Probably the Lua ones are the only ones that will get merged anytime soon. But if people are interested in developing new bindings, we can help you out, or we can have a look at which ones we can get in. And we support a large number of development boards and platforms, daughter boards, expansion boards, and these are Intel and non-Intel. So MRAA already is a kind of completely open library, and I'll talk a little bit about that afterwards. So moving on, the idea is what the API looks like, really what can you do with this library and why is it so easy? So here on the left, we've got the C API. We made a little function here that just kind of essentially sets a GPIO to high. So we take an argument, in this case num, and we initialize a context. So MRAA is based on this concept of context initialization. So here we have a GPIO context, and that really is a hidden pointer to a strut. but we don't reveal how that strut is made. So really, you can only interface with it through this hidden pointer. And once you initialize it with a number or a string, it depends exactly on the API you're using. But here we're using the kind of basic default API. We can set a direction to this GPIO. So in this case, we set its output since we want to set it to high to flash an LED or something. And then we write to this GPIO. And if you've done some Arduino work, you're probably very familiar with this. It's just the concept that we just write one to the GPIO and that sets it high. And then we close the GPIO. And that just kind of cleans up our context and cleans up our memory. If we wanted to carry on using that GPIO, we would need to close it and we would just keep using it. And on the right here, I've got a little diagram that tries to explain, and in this case, it's using the Intel Edison as an example, but on some of these platforms, it can actually be relatively complex to actually do this. It's not super simple. People will tell you, well, you just go into CFS and you just write to this pin or whatever. But actually, on a lot of boards, you have to do little tricks and things that aren't necessarily very obvious or trivial. And in the Edison case, there are things like muxes, but at the base of it, there are actually these sock modes for pins. And here's a little table showing you which sock mode you would need. So in this case, we took like pin 28. You would actually need to go in sock mode 0, which is in this case the only mode for that pin. But on some pins, you can see there's like 3 different modes. So it starts getting a bit complicated, and we don't really want to show that to users. The idea is that our library really abstracts that from the user. You ask for a physical pin on your board, and you really get to interface with that pin. Now, our C++ API is even easier in a way. Here we move from the context to objects, and we do this through a C++ header-only library. And really, this makes it even easier for users since we just have a bunch of methods in the object that you can call. In this case, we do exactly the same thing, except this time it's GPIO8 and hard-coded. And we set the direction to output, and then we simply write to that GPIO. Obviously, you need to clean up the object with the destructor instead of doing the free and things like that. But it works exactly the same way. Now, we then extend that object API into Python. And the Python API works very, very similarly to the C++ API in that it's fully object-based. And it's actually generated using Swig, which is a binding generator from the C++ APIs. So really, we don't actually write any real Python code. We basically generate this API from our existing C++ code. This makes it much easier for us to maintain. But as you can see, it looks relatively Pythonic. Here we import the MRAA library as a global, and we basically ask for GPIO8. We set the direction to output. We write 1, and then we dereference the object. And because it's Python, our garbage collector will go and clean up after ourselves. And that's why we kind of have this memory is not my problem. And that's really the nice thing. Now, obviously, we have our API, as you've seen, is synchronous. But we also have, mostly one asynchronous call. And that's really the interrupt handler. And interrupt handling in MRAA and user space on Linux really is a very high-level interrupt. It's not a low-level interrupt. So you can't really guarantee when it gets fired. We're in user space, so we have no real-time guarantees. But this is how it works. So we can define a Python function. In this case, it just prints a string. And then we initialize a GPIO again. We set it to input direction this time. And then we set the edge for that interrupt when it's triggered. So in this case, we set edge both. And when any interrupt, either high or low, is rising and falling, is triggered, we call that hello function, and we'll end up with this function call. So hopefully we're still relatively easy territory. Now, one of the things that people often ask is, well, okay, so you have this unified API, what's the advantage? So really, hopefully in a simple term, I'll show you why the advantage is. So one of the really cool things we have is because we have this MRAA IO API that's relatively standardized, we can have multiple implementations. And here is our JavaScript in-browser implementation. And it's basically a little simulator. And what we can do is actually initialize a GPIO as you saw before. In this case, we called it M, and we initialize GPIO 13. And we can basically set the direction. And then we'll just set it to go high. And in this case, it goes red to symbolize high. And we set it to low, it'll go white again. So through this little demo, you can see very quickly that, it's really nice. We have this abstracted API, so then we can have multiple implementations of MRAA, and we can do the same thing on any board. And obviously this code, you could actually run it in here, but you could move it to your platform. And if your platform is supported by MRAA, pin 13 would also do this on your actual hardware platform instead of doing it just in a browser window. So you can see this is a nice way of making portable code. And we have a real JavaScript implementation, not just in here. Now, the other thing this allows us to do is write sensors, and that's really where the value of MRAA comes into play. As soon as we have this unified layer and abstraction on the bottom, we can put things on top. And the really cool thing about UPM is that we basically provide a bunch of sensors, sensor drivers at high level for essentially all your needs. And we have a lot of them, and they work on all of our platforms that support MRAA. So let's have a little look at them. And for example, I recommend my favorite temperature sensor, and everyone should have a favorite temperature sensor. I think it's a must in this world. In this case, it's a pressure, humidity, and temperature sensor. But it's really quite nice in that we basically give you a description of the sensor. We give you a link to the data sheet so you can go and get the resources directly from Bosch. In this case, it's a Bosch sensor. And we have the API basically in different languages. So we can look at the C API, and here we get the oxygen documentation for that sensor. We actually have here we get the little code samples, the different languages we support. So you can see it in Node.js, you can see it in Python and Java. Then you can go on GitHub and go actually see the code samples for real. And then we give you a few little hints, depending on which platforms, on some specific things that may be required, or some little quirks of the platform, which may mean that sensor may not work quite as easily. And so the aim of MRAA is, as soon as you support MRAA, you essentially get this UPM sensor library for free. And so hopefully it speeds up your development. You can move from one board to the other more easily. And it gives you a kind of quicker time to development. You can go and see if your sensor is supported, and if it's not, you can actually contribute to the library to support your sensor as well. So that's the unification part. And that's relatively what I talked about, so I'll skip this slide, even though it has a really cool mongoose on it. Here are some of the supported boards that we support. And as you can see, there's some Intel boards, non-Intel board. We support things like Raspberry Pi. We support BeagleBone Black, a bunch of MediaTek platforms. We support obviously the Intel platforms, including things like the Motherboard Turbo, the now cancelled Galileo and Joules, but also the Up Squared, NUC boards, a load of different boards, a load of different carriers, and including things like USB connected Arduino boards via Fermata, which I won't talk about, but it's kind of linked to our talks that we'll have afterwards. And we support basically manufacturers or anyone's adding boards to our project. And so actually we've been working with Lenovo, with MediaTek to add support for some of their boards. We support very, very small maker boards like the Banana Pi. So we're really very, very open in what board we support. It's not at all just Intel. So it really gives you a flexibility of moving from one maker board to another if you so desire, or moving to some of the professional boards that we have with really industrial grade CPUs and I/O connections. And we have three ways of adding boards. So we have what we call the raw mode, which is essentially the default way of adding a platform in MRAA. If a platform isn't supported, you essentially get just raw access to the I/O. And what we mean is that, like what we saw in the CAPI description before in that table with the Edison, in raw mode, you really get what the kernel exposes to us. So when you ask for GPIO 13, we will ask the kernel, well, give us the GPIO that you consider a GPIO 13, which may actually be the GPIO number 255 on your board. But we don't know that. And that's the raw access mode. It allows you to do quick testing. It allows you to write new platform configurations. And it's kind of the basis of how MRAA works, especially on Linux. Then the C platform configurations, which is really a way of adding a board correctly in MRAA, is essentially a strut, which is a MRAA board T strut. We allow basically people to write their own strut. We have a way of basically choosing the platform. And once we do that, we map the I/O functions to their real position. So for example, your I/O that was actually 13 in the kernel and it's 255, we'll go map that correctly. So when you ask for GPIO 255, it actually gives you IO13 in the kernel. And depending on which kernel you load, this might be different. So we'll have some logic to switch that around. Or in some platforms where there's weird hardware things that we need to do, we'll do those first and do it the right way. Do some initialization of the configuration that needs to be done, checking the versions of things. Do you actually have one daughter board connected? Do you have another daughter board connected? So we'll kind of try and work that out for the user and make it as easy as possible, so that when he asks for GPIO 13, we really give him a GPIO 13 that he can see on his board, so we don't have any necessary reading of data sheets or complex work. Now, our third method, which is relatively new of adding board, is for our JSON file. So we have this concept of a JSON file which describes the basics of a board, and we can load these at runtime into MRAA, and MRAA will essentially switch itself to use that configuration file. And really, this is basically the MRAA board tstrut, but filled in via JSON. It's a bit more simplistic. There are some things that we can't quite do. But for most simple boards, this is actually a very nice way of supporting them. Things like the Middleboard Turbot and some versions of the Raspberry Pi can be supported entirely like this without any extra work. So it's kind of nice and easy way of doing it as well. Now, moving on to really the crux of this talk, which is around how to basically integrate MRAA and add a security layer on top. So when we talk about security layers, here we talk about Linux user space security, and we're talking about essentially, do you have the permissions to write to the I/O, and who decides you have the permissions to write to these I/O? Now, typically in Linux, by default, these I/Os are only writable if you're the super user. So the typical way of basically giving people access is, well, we take the dev I2C node and we change the user so that, or add it to a group which the user has permissions to write to. And this makes it quite nice and simple. We can relatively easily add ourselves to that group. But obviously, when we give a user access to dev I2C1, he can then access any device on that bus. That doesn't stop the user going and accessing if we have 3 sensors on it, and we only want to give him access to the BMP280 to get his temperature, then we actually have given him access to the whole bus, which may be more things. So obviously, this is problematic. And one of the methods and things we worked with MRAA with Google, so on the Brillo project, they had this exact problem. And the way they solved it is with this thing called Peripheral Manager, or PIO. And the way it works is Peripheral Manager is a system daemon, so it runs with elevated privileges and has access to all the IOs coming out of the kernel. Now, then the way the permissions are handled is through binder. So applications register which IO they want to use, and actually they don't directly communicate to the Linux kernel, but rather they communicate to the Peripheral Manager first through the binder. And what this means is a user will request not just dev I2C1, but will actually request a specific hardware I2C address on dev I2C1. And if they have been granted permission through the XML configuration file, because this is an Android app after all, then the binder will allow them to basically connect to the Peripheral Manager to actually do that operation. And one of the issues that we worked with Google on this is so they had this Peripheral Manager and they had a few examples of how to use it, but they didn't actually have really many sensors. So what we did is we ported our MRAA layer rather than porting our sensor layer. So what this allowed us to do is, once we had this MRAA abstraction layer on here, we could add any of our UPM sensors on Java on top of MRAA. And this meant that any of our sensors that you've seen on the UPM website could be loaded inside an Android Things device. So the way it works is kind of like this. We have our application, which is written in Java. Then we go to our MRAA Java bindings, and our Libmraa, which is a link to the MRAA Java bindings, has a Peripheral Manager backend. And this backend, instead of actually going to talk to the kernel, goes and does exactly what you expect, which is talking to Peripheral Manager. And because this is running in the same context, when Libmraa actually goes and asks something from the binder, if it's not allowed to get it, it's just going to get refused. So we cannot do anything outside of the scope that's been determined for this application. So really our security context in this case is this blue little box. And any operation outside of that is going to get refused. So That was our first attempt, which working with how do we the security. Obviously, the security at this layer is really very much inside this binder and peripheral manager. It's what the application has been determined to have, but it's not in the kernel, and it's certainly not in Libmraa. Libmraa is only a library you link against. We cannot basically have any real security inside there. We can't say, we can't hard code which users are going to be able to call which IO and things. That wouldn't really work. So that was the first thing that we did. But obviously, this only really works for Android things and maybe some other Android variants, but it requires the binder and peripheral manager and things. So what we tried to do is something a bit more generic. And this is where the AFB bus comes in and what we did with the AGL group. So a little bit of background in the application framework binder and what it does. So it provides a way of connecting multiple applications together through the use of services. And it's kind of like a microservice architecture, but it's a little bit different. I would say between microservices and dbus, if you guys are aware of that. And the way it works is it provides the application, each application that runs its own binder process. And the binder, you communicate to it through JSON messages. And it has a few JSON helper libraries. They're actually very nice, which I'll talk a little bit about. And each application runs in its own security context. And these security contexts can either be a container, it can be actually a complete CPU, it can be its old Linux distro, it can be various things. But the idea is that the locally connected binder exposes a number of bindings, and these really are services. Now, the cool thing is that the services can actually be local services that are running it within that security context. But more interestingly enough, they can be services that are running outside of that security context, completely outside of it. And essentially, if you have permission to talk to that service, it will be exposed locally as a service you can use. So here's what we did. We took the binder and we made this AF-MRAA binding. Yeah, sorry, the terminology starts getting a little bit confusing. And the way we talked to it is we made an AFB backend inside Libmraa. So we made our application, we linked against the standard Libmraa library and did our normal IO calls through it. And instead of actually talking to the kernel directly or anything else or binder or whatever, we talk to this AFB daemon, which is our binder. And inside it, the AF-MRAA binding is loaded, and that is actually linked against a normal version of Libmraa. And this is really where it gets interesting, and that actually in this use case, we're running two versions of Libmraa. One actually talks to the Linux kernel directly, and it has our platform knowledge of what really the hardware is. And the other one really is the AFB backend, which has no knowledge of actually the platform we're running on, just has generic knowledge of talking to our binder. So our application will ask for IO13 with this AFB backend. It will talk to the binder daemon and the AF-MRAA binding service to request IO13. And the real Libmraa will say, okay, I'll go get that for you. And in the kernel, this could be, again, 255 to use an example, and come back all the way through the chain and say, okay, here's the IO, you're allowed to access this. Now, obviously, in this simplified diagram, we only have the security context that we're running our Libmraa library is the same as the Libmraa library with the AFB backend. So this provides no real additional security for anything, since binder is running under the same user as the application. But as we talked through before, the advantage of this service is we can actually run our bindings on a different binder inside a different security context. And this is where it gets a little bit confusing. So hopefully I've not gone too fast and people have been able to follow. So our application in this case uses a UPM sensor and talks to our Libmraa binding with the AFB backend inside its own security context. And obviously its locally exposed binder actually doesn't really have a binding that runs inside it, but rather communicates to another binder which does have a service inside it. And so that binder exposes AF-MRAA binding through this magic bus that the binders have to talk to each other. Now, this binding links to the normal Libmraa, and in this case, we use the Fermata backend, which makes things a little bit more confusing, but it kind of shows you the flexibility of the beast. And this runs in its own security context. So any calls that Libmraa makes, it's run in a different security context than what your application did and took to its Libmraa with the AFB backend. So it's really kind of two very distinct processes, and they only communicate from one binder to the other. But this is abstracted at a programmer's level. For them, they've only written their application and used the UPM sensor. They shouldn't even necessarily be aware that they're actually not talking to the IO directly, but actually going through a binder process. This is completely abstracted for them, and they don't have to touch the binder that talks to a Libmraa. Now, the reason I made this a little bit more complicated is because this works in a little funky way, and it shows the flexibility in that here we have a backend of Libmraa which talks to Fermata, and Fermata is a way of talking to basic IO protocols to a bunch of small devices. And in this case, I was using an Arduino board, which is quite nice and simple way of prototyping. Oops. And this is you communicate to it through a UART on the Linux kernel. So actually this Libmraa talks to the local UART in your kernel, and that UART is connected to the Fermata board, and that's where the IO is connected. So when you ask for GPIO 13 in this, you actually go and flash GPIO 13 on your Fermata connected board. But as far as the user is concerned, or the application developer is concerned, he really only wrote his application, talked to his sensor, and that's it. The whole other chain is done in the background. Now, obviously, if the application is run and we did not have the permission to go and access the I/O, we'll just get a refusal, and a nice little error code will be pushed back to the application so that they can handle it. Now, so one of the things the big thing that we did was basically integrating the AFB bus as a MRAA backend. And here I'll talk a little bit into how the backends work and how you configure it. So MRAA essentially started off with supporting weird kernels and boards that weren't well supported. And so what we did is we had this way of overriding the default functionality. So when you actually ask for GPIO 13, instead of just going to 255, maybe we could go and check something else, do some weird operation, set a register somewhere, and then do the operation. And so every I/O call you make in MRAA can be overridden by the platform. And that's what we started using to do supporting Fermata boards, the D2XX driver, peripheral manager, and all. So instead of talking directly to the kernel and having this nice kernel API, we said, well, we don't always have this nice kernel API. So what we'll do is abstract it all away and say, depending on the board, we'll do different things. And so we're able to actually do a different operation on any single MRAA call. So when you do MRAA new GPIO on a certain board, it'll actually behave something completely different on different boards. But as the developer, it'll always do the same thing as far as you're concerned. So that's really the mechanism we use. Now, the AGL platform is we have two types of platforms. Typically, when you initialize Libmraa, it goes and guesses the hardware you're on. But some platforms, we either don't want to guess, or we consider it that it's kind of, you'll always go through the same thing. So the AFB platform is actually a hard-coded platform type. We have a few of these, but the most common is probably the AFB or the mock platform, which is kind of our test bed. We're able to basically do mock calls, and it basically goes and logs to syslog instead of actually doing any real I/O operation. It's nice for testing internally. But the AFB platform is configured with this build arch flag in CMake. And this means that whenever you'll actually do an I/O call, instead of actually going and talking to the kernel, this won't talk to the kernel at all. It will make a request to the AFB bus to your local binder to talk to the AFMRAA binding. And if you don't have this loaded, it's essentially be a completely useless library for you. So you have to know a little bit how to configure it. Now, the AGL platform, really what it does is it overrides all the functionality in MRAA. So like we talked before, things like MRAA I2C init will no longer talk to dev I2C end, but rather it will make this call. So we use the AFB WSJ library. And this is the asynchronous calls that we actually use to talk or to send our JSON message across to our binders. And in this case, what we do, because most of our calls, like I talked before, are synchronous, we actually synchronize this asynchronous call which is a little bit nasty. And we're working with the AFB people to make a call that's synchronous for us. So it'll be a little bit easier. But here's kind of an example of how it goes through. Maybe a little bit simplistic, but when you make the I squared C MRAA init, you'll actually end up calling the specific board I squared C init function pointer, and then you'll actually call the specific board I squared C init. And in this case, for the AFB platform, this is going to be different than what it would be on a Raspberry Pi, for example. But again, as far as a user are concerned of the application, it's going to be the same thing. And for the UPM sensor, it's going to be exactly the same thing as well. So you really have these kind of nicely defined abstraction layers to try and make it easier to write code. And so obviously you notice that the binding for AFB actually had this other library or this binding inside it called AFMRAA binding. And this is what really links against a real Libmraa. And so we call a real build arch. And our build arches in these cases are the architecture types, so x86, MIPS, ARM. And we sort them like this because, well, there's really no point having a binary that runs on ARM and MIPS at the same time. It's not going to work. So we basically try and, by default, reduce the binary size in this respect. But all the build architectures are supported. You link against whatever Libmraa you would like. And actually, you could chain them if you really wanted. That would make a funky demo, but probably not so useful. So you could have multiple AFB backend MRAA talking to each other and eventually doing something else. But it does mean that you do need two versions of Libmraa, two different binaries. We haven't worked out a way of doing this in a nicer way yet. But one links against the AFMRAA binding and the other one links to the application. So typically for the application development toolchain, we'll give you the Libmraa that's with the AFB backend, and so it won't work directly on your kernel. And what we do, and I talked a little bit about this before, is we have this JSON library that we use called wrap.json, which is a JSON-C kind of abstraction as part of AFB utilities. And this is really useful since all of this communication is done over JSON messages. So we use this really nice little library to try and make that easier for us. And I really recommend it. If you need a tiny C library for JSON, this is really, really cool. Moving on to some of the future works we plan on doing. So obviously this is available on GitHub and it's fully open source. It's MIT licensed. I think I skipped the slide that had this on. So you can go on GitHub Intel IT Dev Kit and get all this work. But what we're doing in the future is trying to improve it so that the AFB platform in MRAA has knowledge of the IOs that are supported on that specific platform. So having some way of communicating with the binder to get the number of I2C buses or the number of GPIOs that are available. Right now, we don't expose this at all. So essentially, it works on a permission basis. If you can open I2C0, then it must be there. Otherwise, it's not going to be there. So it's a little bit tricky for users to really use it in a completely abstracted manner for now. But we're moving to sort that out. And our binding itself is a bit simplistic right now. It uses only two, what the AFB bus call verbs. And that's really kind of synonymous to dbus method calls. And we have one for initializing devices, which is really MRAA context, and one for running commands, which is essentially a function call against an initialized context. Now, it would be nicer to have these a bit more split out so you could use the AFMRAA binding directly without actually loading another libmraa. Maybe not so many users will do this, but it'll be one way of removing one layer, which will probably improve performance a little bit. So it could be nice, and even internally for coding, it'll be nice for us. Then I talked a little bit about our use of AFB WSJ1 call S, which we do with a lock and wait for the response. So we basically make an asynchronous call synchronous. And this is a bit nasty and makes our code a bit tricky. So we're trying to work with the AFB guys to give us a fully synchronous call. Obviously, for our asynchronous interrupt calls would be really nice. And obviously, some of the IO operations you do may be asynchronous in the future. And then the last bit is currently we only support actually I2C on the AFB platform, and this is mostly done with time. So we're trying to get some feedback from various stakeholders, and based on the feedback, we'll do the other IOs after that. Once we've really sorted 100% what we want to do for I2C actually suits everyone's needs. So you're more than welcome to try it out, give us some feedback, and hopefully the other IOs will come really quickly once we've decided that really is the way we want to go. So that's it really. So thank you very much. And like I said before, the codes are all available under an MIT license, fully open sourced. It's available on GitHub on the Intel IoT DevKit page. And here we have MRAA, UPM, the AFMRAA binding. We have a link for the UPM website here. We have a Freenode IRC channel. You can come chat with us. Hashtag MRAA on Freenode. And we have a public mailing list, so you can send some questions. You can also do this on GitHub issues, no problem. Yeah, please get in touch. And if you have any feedback on MRAA or the AFB platform in general, we'd be more than happy to discuss it. Thank you very much.